Hello dear students, Assalamu alaikum. Today we are going to discuss about pulse width modulation and its techniques. Our agenda is what is basically a PWM signal and why we are in a need to use in our electronic systems and circuits, especially for power converters, and how the signal PWM signal can be generated. Okay, so basically pulse width modulation are the square pulses, and they are used for reducing the average power which is directly delivered to the load. The method involves the chopping of discrete chopping the signal into discrete parts basically. So PWM has two states, one is on and another is off. So when we are discussing the on-off states, so we can relate them as zeros and ones like in binary. Okay, so the average power which is delivered to the load can be controlled by turning on and off the time period of the control switch basically, which we are using in the designs. Okay, so if the width of the square pulse is longer for certain time, I mean on for on period, so the higher voltage, the average higher voltage, the voltage will be higher. Okay, so we are going to refer figure 1. So as you can see in this figure that there are there are basically narrow pulses and there are basically some wide pulses. Okay, what does it mean by narrow pulses? That on period is on time is less than this. Okay, so the average power which is going to be delivered to the load is lower. Okay, whereas in this portion you can see this is basically, these are basically wider pulses as compared to these pulses. Okay, so the average voltage will be higher at this portion. Okay, so the PWM can be generated by comparing two signals basically. One is triangular pulse, as you can see, the triangular pulse, and another is the DC voltage. The DC voltage can be fixed either variable DC, and we will get the output, resultant output, which is PWM basically, pulse width modulation. And these generators can be implemented by using operational amplifier ICs basically. You can use the very common IC 741 for this purpose. Now I want to give you some brief details about the circuit design of this PWM. Okay, so and I just want to tell you in this lecture that our next lecture will be on PWM controllers basically, which are used in switch mode power converters basically. Okay, so I'm going to switch over my control to the simulation software. So I'm going to create a new project from here. It's basically a test project, test project, okay, and then I have to choose the path where I have to save the project, okay. So okay, uh, now I'm going to, as I told you that the OpAmp can be any operational amplifier IC, but I would like to prefer, I would like to use LM358, okay. So basically, uh, um, uh, basically it has 8 pins, as you can see in this PCB layout of this IC, and this operational amplifier has two basically op-amps, built-in op-amps, okay. So I'm using this for 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 my system, okay. So yes, so as I told you that this part A and part B, I'm in the whole package is complete now, okay. So I'm going to pick the voltage source, okay. And since I'm designing a triangular pulse generator, basically it's a start of PWM creation, generation, okay. So I need uh, two power sources. I need basically dual supply, plus and minus voltages, okay. So plus 12 volt and the uh, minus 12 volts, okay, 12 volts, okay. So what I'm going to do is basically this is our main power source. So I'm going to shift over here, and I want to uh, label this, okay. So as you can see, I'm going to write plus VCC, okay. Another point is minus VCC, okay, uh, minus VCC, okay. And this is basically standard procedure to generate, to create a dual power supply source. So this is basically a ground terminal, okay, okay, that's it. Now I want to give the power sources to this IC basically, okay. So I'm going to uh, apply power sources at this IC, okay. Uh, this is basically a plus VCC, plus VCC, and this is basically a minus VCC, minus VCC, minus VCC, okay, okay. And these two terminals, one is this, will be ground, GND ground, and another, this terminal will also be grounded, okay, ground, okay. So now I'm done with the power sources, okay. Now I want to add few more discrete components. Resistor, okay, uh, this, okay, another resistor. Basically, right now I'm uh, generating a triangular pulse out of from these two op-amps. So I need another resistor, so I can put over here, I think. Um, okay, let me do something extra. Okay, so you're we are almost there. Okay, and this terminal will be connected with this, and I need a capacitor, basically capacitor. So I have connected like this. Okay, so I am now giving them values, 2 microfarad, and this may be uh, 15K, and this can be 1K, okay, and this can be a 220 ohm, okay. uh, okay, and then this terminal will be connected over here. Okay, now I'm going to test this circuit that either it is generating triangular pulse or not. So I have to just verify it by connecting oscilloscope. Okay, so as you can see, I'm getting, you know, a triangular pulse. Okay, I'm going to switch off these other, you know, uh, channels of my oscilloscope. Okay, so as you can see that I'm getting you know, triangular pulses. Now this will be the start of our PWM creation, basically. So I'm going to stop the simulation over here. One thing more, I want to tell you that the the frequency of this triangular pulse can be controlled with these two devices, I mean two discrete components. Okay, if I will increase the value of this capacitor, okay, so the frequency will be reduced. Okay, as you can see, the the, the time period is longer, so the frequency is reduced. Okay, if I reduce this capacitor to, and and the and the uh, this 10K, so what is happening over here, the frequency is increased. Okay, so again, if I am, you know, uh, increasing the value of this uh, resistor, I am decreasing the frequency of this triangular pulse. Okay, So now I am going to do uh, another step. Okay, so I need another basically OpAmp where I will compare these two signals, as I told you that in my uh, uh, slides, that we are comparing two signals basically. One is DC, a fixed DC, or the variable DC, and one is this triangular pulse. Okay, so first of all I have to supply the power to this IC again. Uh, okay, so this is our plus VCC, and this is our minus VCC. Okay, so basically comparator works with two signals. They are basically comparing um, uh, uh, between inverting and the non-inverting terminal, okay, of the operational amplifier. So if I am going to uh, mm, let me do this. Okay, okay, now for the DC voltage, variable DC voltage, I'm going to connect the potentiometer pot over here. I'm going to pick active pot. Okay, so this, and these two points will be connected with the supplies basically. Okay, plus VCC and the minus VCC. Minus VCC. Minus VCC. I'm giving the plus and minus supply over here just because the triangular pulse is going into positive and the negative, and I will also show you in the oscilloscope as well. Okay, so that's it. I am going to connect oscilloscope at this terminal, output terminal. Okay, so I'm connecting this. I'm also connecting the triangular pulse, and I'm also connecting the DC voltage supplied to this comparator. Okay, so this can be like this. Okay, so I'm going to start this. As you can see, there's basically a triangular pulse, and the so the okay. Uh, I'm I have to connect this with the with the with with 5 volts. Okay, because my signal is, you know, smaller in peak to peak. Okay, so uh, uh, 3 volts. Okay, 3 volts will be fine. Okay, so this is basically minus 3 volts, Okay, have to, I think we have to, okay, okay, I'm going to off these two, even now I'm going to off this, okay. So oh, one thing is missed. I'm so sorry. Minus VCC. Okay. So we are here. Okay. So why I connected these two terminals with 3 volts basically. Uh, I want to tell you uh, that let's suppose I'm going to turn off this and going to turn on the channel B basically. As you can see that the uh, peak of this is 2.7 volts and uh, uh, the another peak is minus and minus 2.75. So I have supplied 3 volts with this 3 volts. We are comparing the triangular wave, okay, and the output of this is basically I think I'm missing something. What happens? Minus VCC plus VCC. Okay. These are 3 volts. These are minus 3 volts. Fine. And the I think something went wrong with this triangular pulse generator. Yes. So if I switch back to 15K and rest is fine. Ground. Okay. What's the wrong? Let me verify. Okay. Okay. If I will have to connect this directly, maybe this may be the problem. We are going to connect directly with this. Channel B. Okay. If I disconnect this from here, this from here, and this from here, and I simply connect here. What Oh, I'm so sorry. Actually, I switched off the uh, uh, oscilloscope. I'm so sorry about this. I'm going to revert my settings. Okay. Okay. So okay, that's fine. That's fine. That's fine. Okay. So as you can see, over here, uh, basically I want to also connected the DC voltage with the channel C. So I'm going to again switch on the channel C, and I need to configure this basically, um, 0. Where is 0 reference? Okay, this is basically 0, and I have to make this as 0. Okay, so I'm going to do this. Um, this is 5 milliseconds. 5 milliseconds. This is 5 milliseconds. Okay, so now you can observe, you can I want to do this. Okay, and then the DC. Okay. Okay. So now you can observe in this that the the these these are basically the triangular pulses on one terminal of the comparator, and the DC voltage is on another terminal. So it is basically comparing. Okay, so if the width is higher, okay, so the pulse in positive side, the pulse will be this, and this is basically a dead time. Okay, so this is basically off time, off period. So you can see this portion is turned off and this portion is turned on. Okay, so I'm going to uh, change the uh, uh, potentiometer value of DC basically. So what happens over here, this DC voltage, has been shift. Oh, one thing missed. I'm so sorry. Actually, I'm so sorry. Okay, now I'm almost there. This is basically off time, this is basically on time. You can see in this clearly that the on time is this is basically on time, this is basically off time. Okay, so if I go back over here, and this is basically and I should stop this over here for your understanding. Okay, so as you can see, this is basically wider area which is off. Okay, and the smaller area which is on basically. Okay, so I'm going to switch to the auto mode of the oscilloscope, and I'm going to reduce the value. Okay, so the off time is reduced again. Off time is reduced in terms of these two comparing signals, and the on time. Okay, again I switch over here. The off time is shorter. The in positive terminals, I mean in positive side, the this is basically on time, and this is basically off time. So so as you can see, these PWM signals can be generated in this way. Okay, so this is basically the concept of you know, creating a variable PWM signals. Okay, if I do this for your understanding, I can maybe show you clearly. Okay, so as you can see, if I am changing the potentiometer basically, so the pulse is changing. Okay, if I'm going to change the DC voltage level, I'm in a state to change the width of our pulses. Okay, fine. This is basically a shorter time, this is basically a longer time. Longer time is off and shorter time is for on. Okay, so this is the very beginning of our you know, PWM converters, and PWM converters or switch mode power converters are very much relying on these pulses. So our next lecture, as I told you, that will be about the PWM controllers, that how they are you know, are used in power converters, and how they can be used as either DC-DC converters, either in DC-AC converters. So my next lecture will be on those controllers. For today, this is the end, and thank you.